Good morning, everyone. It's really a pleasure to be here. I want to thank Stefano and Vito, a chance to hear some really interesting science, also to come to Venice, to reconnect with people. That's, we realize how important that is to have the informal interactions, and this is really a pleasure. So it's great that we're sort of back to normal and that I can tell you about our work. I'm going to talk about spin-orbit torques in antiferromagnets, so continuing a theme. And this work is actually involving quite a lot of people. You'll see it, their names on the papers, and I'll tell you about them later, particularly Ege Kogulu, who was a PhD student who did most of this work, along with our collaborators, Hendrik Oldegg and Ramesh at ALS. So we're looking at trying to manipulate antiferromagnets with spin-orbit torques. And let me move up forward. So I'm going to tell you a little bit about our motivations, an introduction, and I'm going to tell you about two experiments we're doing. One is to try to directly view what happens to an antiferromagnet when you put a current. How does the domain structure in the antiferromagnet change? To go beyond resistive measurements to see what's happening to the domain microstructure. And the second part involves trying to quantify the torques that act on the antiferromagnetic order. So to extend the techniques that have been used for ferromagnets, particularly these harmonic measurements, to antiferromagnets. So let's talk about the introduction. So one of the, say, goals of our work, and I know many others, is to make oscillators. We want to be able to use the fast dynamics of an antiferromagnet to generate oscillations in the terahertz range. We know the inverse process is possible. We heard about this yesterday and the day before, that you can excite dynamics in the antiferromagnet and create a current, a spin current. So the question is, can we get to the point where we impinge a spin current on an antiferromagnet and excite terahertz dynamics? So can we make an auto oscillator that's an antiferromagnetic oscillator? And we know there's several theoretical works, Ran Chen's work with Arne Bratas, and also Andrei Slavin and his collaborators have nice theoretical ideas on how this can work and how you can generate terahertz signals with this. And the application idea is that there are very few narrowband sources and detectors in the terahertz range. This is kind of a gap in our ability to detect radiation. In particular, in the terahertz range, mostly people use bolometers. So you're using some kind of a thermal effect in some sense to detect. If you had a oscillator, you could have a narrowband detector, and ideally you could adjust it so you could detect different radiation even with the same device. And this would be useful for a number of things. But we're really interested here in the fundamentals. Can we understand how torques act on antiferromagnets, and what would we need to do to get to making an oscillator? This, maybe I don't have to belabor this point. The point is that with antiferromagnets, it's always hard to act on the antiferromagnetic order. We heard this morning from Thomas's talk very beautifully. There's really, you need some leverage. A magnetic field can provide leverage if there's an excess moment. But one neat thing about the spin torque is that if you apply a uniform spin current on an antiferromagnet, from the point of view of the antiferromagnet, if you think about the damping-like or Slanczewski-like torque, that looks like an alternating field. So uniform accumulation, if you think about it in terms of the dynamics, looks like the field on the sublattices A and B alternate. So you can potentially have a very effective action of a uniform accumulation on a antiferromagnet. You also have the usual spin torque can usually be divided into two components. One is the field-like and one is the damping. So you can also have this field-like component that acts on the... and we know that there's some beautiful experiments that show evidence of switching. And we heard about this morning in copper manganese arsenide. By applying currents in different directions, you get changes in the resistive signals. Often these changes are different than what you see in a ferromagnet, where you can see clean switching from left to right, up to down. You see something that more looks like a charging effect, you could say, like a capacitive effect, where you put more pulses and you get larger changes in transverse resistance in this case. So there's been also work on insulating antiferromagnets. That's the topic here, iron oxide, alpha iron oxide hematite. There have been experiments that show evidence of switching with electrical studies. There's also been experiments that show absence of evidence. That is, you remove the antiferromagnet, and you can get very similar to resistive signals than what you see in the switching. So Qilan Chen's group at Johns Hopkins has shown this with nickel oxide and removing nickel oxide. Jeff Speech's group has shown this as well. So there's basic questions about what's really going on when you put a current pulse, and is it a structural or electromigration effect, or is it a magnetic effect? So, okay, we're going to work with iron oxide. This is a nice material in that it has a small excess moment due to DMI. These are all the same things that people have already said, so I won't say them again. But the key thing here is we can manipulate the order with a modest magnetic field. So we can orient the Niel vector in different directions. And that allows us then to explore effects. So it's really the fact that we have this, we have a nice hexagonal structure. In principle, there are 3 easy axes in this hexagonal plane. And the pulsed experiments have involved pulsing the current along different directions to favor different easy axis directions. And you can use the magnetic field to rotate the Niel vector. The Niel vector rotates perpendicular to the field, the so-called flop configuration. So the excess moment is perpendicular to the Niel vector. And so in a modest magnetic field of about 1 Tesla, you get a beautiful sinusoidal response to a magnetic field. And essentially it saturates until you get to very large fields when you start to cant the magnetic moments. So this can provide some calibration and also a lever to detect the changes. So if you apply pulses, for example, along different axes, you can find these resistivity levels and compare them then to the resistivity levels you see by rotating the magnetic field. And then that allows you to deduce which axis the Niel vector likely ended up in. And interestingly, in these experiments, the actual Niel vector ends up along the current direction. At least that was what was inferred in the experiment. So there are 2 parts to this talk, as I mentioned. One is imaging. Can we really confirm that these changes in resistance, in Hall resistance, are due to changes in the antiferromagnetic order? And of course, we'd love to know the mechanism of that change. That would be the ultimate goal, to understand the interactions that are leading to those changes. And the second part is, can we quantify the torques? What are the nature of the torques that act on the antiferromagnetic order? So you've heard nice talks this week about imaging at ALBA, which we've done also. But this is now, we're talking imaging with X-rays. This is at the ALS. We're going to use dichroism. In fact, for antiferromagnets, we're going to use linear dichroism to get at information about the Niel order. So for XMCD, you see a change in contrast when you have changes in the projection of the magnetic moment along the wave vector of the light. And for antiferromagnetic systems, there's a linear dichroism effect that allows you to see changes in contrast with respect when there's a difference in the Niel vector orientation along the wave vector of the light. So we're looking at contrast that's of this form, a Niel vector dotted into the polarization squared. There we go. Okay, so, let's see, yep, we're going to come back. This is the problem of being too impatient, which most New Yorkers are. So this is an photo emission image. So we're collecting electrons. The electrons are giving us information on the absorption at the surface. And we have samples that are in the form of Hall bars, where there's platinum in regions, a few nanometers of platinum, 30 nanometers of iron oxide. And the bright regions are the regions which are uncovered iron oxide, so you see more contrast. And this is domain structure. The black and white regions are domain structure, and if you look carefully, the domain structure goes actually through under the platinum. So there doesn't seem to be an interruption of domain structure in or out of the platinum. We're outlining the contacts here. And what we decided to do is take pattern. We saw that the domains are about a micron in this sample, maybe half a micron to a micron. What we decided to do is make Hall bars that are on that scale, so just several microns in size, so that we'd be close to the limit where we're just able to act on several domains. So the idea is, could we switch the domains that are right in this region? So these are the metallic regions, again in this multiple cross region, and we're looking to see if we can act on those domains. Okay, so we have two polarizations we can interrogate the system with. One is pi, and the other is sigma. Sigma is completely in plane. Pi has both in plane and out of plane components, so this lets us try to unravel what's happening in the experiments. And this is our sample. We've cut one part. We can only actually have 4 leads in the experiment where we're at the ALS, so we can apply pulses along 2 directions, A and B, and then we can image after the pulses. Or what we do is we image after multiple pulses, which is like the experiments, the electrical experiments. And here, to confuse people, we've inverted the contrast. Now the metallic regions are the bright ones, and the dark regions are the iron oxide. I looked at this so much I didn't even realize we actually had inverted the contrast. But you can see then clearly the path the current is flowing. And we could use the same sample to see the phenomena that was seen electrically. We can pulse, and we see changes in the Hall resistance when we change the direction of the pulse. Again, we apply multiple pulses, and after each pulse, we measure the resistance. In the X-ray experiment, we're going to apply multiple pulses and look after the multiple pulses. So again, the goal is to correlate this resistive data with changes in the antiferromagnetic order. So one puzzle got us to go back and look at the equilibrium response. So we've just taken a sample now, a homogeneous sample without patterning, and put it in the beamline and rotated the sample. This was to try to understand what are the equilibrium directions of the Néel vector, and how does the contrast change. So sigma polarization, again, is in plane. If you have the Néel vector in plane and you rotate the sample by 180 degrees or reflect it, you should come back to the same image because you're imaging p dot n squared. If the Néel vector is in plane and you have an out-of-plane component of the X-rays, this pi polarization, you also should come back to the same image after 180 degree rotation. So one of the things that puzzles in our experiment was that when we did a rotation of 180 degrees, we didn't come back to the same direction. So we could then deduce that there's an out-of-plane component to the Néel vector, at least at the surface, maybe through the bulk. We don't know, but there is also, and this is part of this is important in understanding the switching, that it's present without a current, that we have both in-plane and out-of-plane components. Okay, so this is one of the first experiments we did, just pre-COVID. We start in some initial state before we've applied any current. Again, you see the Hall cross. This is the cut. We apply a pulse along A, so along this green line, and we see some change in contrast here in the arm where the current was flowing. We apply a pulse along B. That part stays, and now there's a change in contrast along the current direction in B. And we apply a pulse A, and we come back to this state. So we've cycled, and we see there's some changes here that are only initial, that is irreversible, and there's some changes by going back and forth that we can change the state of the antiferromagnet. So this tells us that indeed the current is changing the state of the antiferromagnet, but it's not as straightforward as in a ferromagnet case. So we can see more clearly what's happening by taking difference images. So this is after the initial pulse. We've changed something in the arm. After the second pulse, we come back, we've changed the domain here in this, and we can come back to the original state. So we have irreversible and reversible changes in the areas where current is flowing, and we also see changes even outside, which I'll come back to in a moment. So these are what can we learn from this experiment? We've learned that resistance changes are associated with changes in antiferromagnetic order, that only a fraction of the domains actually switch, which is consistent with also the electrical data. You don't see the full change in resistance. And there's irreversible and reversible changes in the domain structure. So sometimes just one of changes. Now, if you go to higher current, things become even more interesting, you could say. You again see these kind of changes that are reversible in the region, and you start to see changes in areas where there's no spin currents. So we can say that this spin is not the only ingredient in these experiments, and in fact, you can switch regions that are in proximity to where the current flows. We also looked at the polarization. We can do an analysis of the polarization, so we can analyze whether there's a change in in-plane or out-of-plane component by separately analyzing the sigma and pi polarizations. The top row is the sigma. You can see that there is a change in polarization in plane when you pulse from A to B, this region here. And we also see changes in out-of-plane component. So this was the big surprise, that we have both in-plane and out-of-plane components in what's nominally a hexagonal system with the C-axis oriented film. And so what we come up with is the following picture of what the switching might be like that is consistent with our X-ray imaging data, that when we pulse from A, we end up with the Néel vector rotating in this direction, more or less along the current direction, and when we pulse in B, we end up with the Néel vector along, again, the pulse B direction, and there's some out-of-plane component, so there's a change in the projection of the Néel vector along the out-of-plane along this pi direction of the X-ray. So this was our best guess as to what is happening in the sample. So these are our conclusions, that you can have that you can change the domain structure. We see in-plane and out-of-plane components even in equilibrium, which was unexpected, which I'm open to ideas on how that can be. It could be strain, it could be something at the surface, and we can see that we switch domains with spin torques, and we have reversible changes and irreversible changes. And we note that the symmetry is really not what's expected of spin torques. It's really the Néel vector ends up along the current direction. So this was a puzzle. It seems to be more consistent with magnetoelastic effects than spin torques. So I realize I'm taking time, but I want to say a few words about our recent experiments, which are quantifying the torque. These are harmonic Hall measurements. And the goal here is to really see what are the torques that act on the Néel vector through perturbative measurements, not switching, but low current measurements where we apply an AC current and look at the changes in Hall resistance in response to the current. So we're designing a sample, again, a Hall bar a little bit bigger, 5 microns, same type of samples, 5 nanometers of platinum on alpha Fe2O3. And we're going to use the SMR, which has the symmetry like a planar Hall effect. We apply an AC current, and we look at the linear response, and we look at the second harmonic. And the second harmonic is what has information on the changes in order. So to get some feeling for what you'd expect, this shows a modeling of the spin torques. First, just an external field. So if you apply an external field to an easy plane magnet, we're neglecting the small easy axis in the plane. The Néel vector ends up perpendicular to the external field. So this is what's going to give us also our leverage, because we have a small excess moment that makes a small field easy to reorient. If we now have a field-like torque present, the Néel vector ends up oriented perpendicular to the net field, the field-like plus the external field. So you can see that if you have a spin effective field like torque, and the field is in plane, that's going to rotate the Néel vector in the plane. And that you can detect through the SMR, through the harmonic measurements. If you have now a spin torque effect, the first effect is you'll have precession, and the equilibrium will be, for small torques, will be the Néel vector along the spin accumulation. Which state you end up with, plus L or minus L, depends on the initial state of the Néel vector. If you have a large torque, you'll end up making an oscillator. This, remember, was our goal, where the spins now precess perpendicular to the accumulation. So this would be our terahertz oscillator. But we're going to look at effect of small torques on the orientation of the Néel vector. So the picture is you apply an AC current, that leads to an AC accumulation, that leads to an AC torque, that leads to modulations in the Néel vector orientation, that leads to resistance changes we detect via the spin magnetoresistance. And thankfully, we had lots of theoretical help from Ran Chen, and we were able to take the basic form of the torques and derive an expression for the second harmonic signals that would allow us to separate fields from spin torques. And you can see the fields have this form. And the spin torques have a different angular dependence. And the key thing you can realize is damping-like and field-like torques can be separable depending on the direction of the Néel vector. If you do an XY, if you scan the field in the XY plane, you're sensitive to fields, field-like torques and Ørsted fields. And if you scan the field in the YZ plane, you become sensitive to damping-like torques, and this term is 0. If there's small canting, there's mixing of these two of this. It's not perfectly separable, but this is the dominant interactions are separable. So this allows us to then see that by scanning the field in different directions, we can emphasize and quantify different torques. We should note also that there are other components. There's the usual Hall effect and also a Spen-Seebeck effect because we're introducing thermal gradients when we apply. But thankfully, these have different angular dependencies than the torques. So we do these measurements. We rotate the sample. These are experiments we can do in our lab. With just, as you saw earlier, you can get this nice sinusoidal dependence as soon as the field is larger than about 1 Tesla. And you can get these second harmonic signals in the in-plane direction, which have this beautiful symmetry with several components, several Fourier components to the response. I'll come back, I'll look at the YZ scan. You can also see response in the YZ scan that depends systematically on the applied field. And what we do then is try to fit the data. And we fit the data at 3 Tesla. That turns to be the right region for us because for small fields, we don't saturate the Néel order. And for large fields, we start to cant the magnetic moments. So our theory breaks down because we have a big excess moment. That's important. We get actually a beautiful fit for the XY scan, so the field-like scan. We can fit with these components. And we get a reasonable fit with the YZ scan, particularly to the first harmonic. We have to include that we have a small tilt to capture this data, and we get reasonable reasonable fits also to the second harmonic. And the big surprise here, and this may relate to the talk you heard yesterday from Romain Lebrun, is that the field-like torques are significantly larger than the damping-like torques in these experiments and in several others. They're about 2 orders of magnitude. So you can see this almost directly from the data. Here you're getting 0.2 changes in milliohms, and here just a small fraction of a change in the response. So unlike the case of ferromagnets, what we have here is a case where fields, this field is also much larger than the Ørsted field, so an order of magnitude larger than what we compute the Ørsted field to be. So the field-like interactions seem to be much larger than the damping-like interactions for these types of samples. I may not say too much because I know I'm running out of time, but by looking at the field dependence and looking at the different angular components, we can extract a component that's linear in field, which is consistent with an ordinary Hall effect, and we can extract components in the second harmonic in-plane scans that go as the field, which is consistent with the spin-Seebeck effect associated with the excess moment in the iron oxide. And this is the field-like torque, which is predicted to have a 1/h dependence, which again, we fit it at 3 Tesla. At high fields, our theory breaks down. Again, at low fields, we don't saturate the sample. Okay, so we came back to our theory friends. This is Ran Chen, and we tried to understand why the field-like torque should be so much larger. I'm running out of time, sorry. Yes, why there's so much, I only have one more slide, so it's all good, I think. Why they're so much larger. And it turns out in his thesis, he had computed the real part of the mixing conductance, but not the imaginary part. So he went back and computed the imaginary part of the mixing conductance. The formulas were in his thesis and even in his paper with Arne Bratis, but he hadn't done the computation. And what he found is a region of parameter space. J is the coupling between itinerant electrons in the heavy metal and the insulator, and this delta represents the spin flips in the antiferromagnet, basically changes in the order divided by the bandwidth in the metallic region. So for small coupling between itinerant electrons and the moments, you can be in this range where basically where the imaginary part of the mixing conductance is much, much larger than the real part. Basically, we can deduce that if we want to get to large anti-damping torques, we need to increase the coupling or find ways. And this is, by the way, computed for a compensated interface. So it may very well be very sensitive to the types of interfaces you have in these kinds of experiments. So again, a quick summary that we've been able to quantify the torques, and this came out just in June in PRL. We think this is a technique that can be used to optimize the torques and also understand how the interface plays a role in setting these torques. Of course, a key ingredient is to be able to rotate the Néel vector, and that's not possible in every system. You need to be able to do that at relatively modest fields. Okay, this got all messed up, but I said all the points I wanted to say there. I should say our collaborators have also done work on third harmonic measurements and come to a similar conclusion. And with the third harmonic, they can also quantify, this is Fenyan Yang's group, they can also quantify the magnetoelastic effects that are present in these samples. There's a recent experiment from MIT that comes to the same conclusion, that the damping-like torques are several orders of magnitude smaller than the field-like torques. That's from Lu Chao Lu's group. Okay, so I want to thank, these are the people who did the work, Ege Kogulu. I want to thank Osan for sending him to me. Please send more. He was fantastic. He just got his PhD. We worked closely with Ran Chen and Han-Tao Zhang, Hendrik Oleg and Rajesh Gupta, and Fenyan Yang provided these beautiful samples for these studies. And I think I'm done. This is celebrating Ege's thesis, which we did in May, thankfully, all together. Thank you very much for your attention.
Thank you.